Earth Science class, let's go over Chapter 5, Earthquakes and the Earth's Interior. So what are earthquakes? I don't know if you've ever experienced one, but an earthquake is when you have seismic waves propagating through the crust. That causes a vibration, and it's essentially a big release of energy. And earthquakes are very terrifying. They can be very frightening. If you've ever been in one, time seems to contract and slow down, like as if it's in slow motion. So earthquakes typically only last about 30 seconds. Some can last about a minute and 30 seconds, but it's like if you've ever been in a car accident, you know how like when you're about to get into the car accident, everything kind of slows down, time kind of contracts and then speeds up again after the accident's over. It's kind of like that, and it's just terrifying because everything's moving and shaking. You might feel dizzy or disoriented. Okay, click on that YouTube video below to see some footage of an earthquake. So earthquakes are associated with movements along fault lines. So faults can be separations between two different crustal blocks, or you can have actual tectonic boundaries where there is some movement. We live on a dynamic and active planet, and as lithospheric plates move, they don't, we're talking about huge, rigid pieces of our crust. So they don't move very easily. So a lot of times the faults are locked in place. And so it takes a lot of pressure and movement to actually get them to break through and then to have some displacement. So essentially what happens is the rocks along the fault will deform, and they'll deform because the plates want to move in those certain directions. And then as the plate makes that movement, the rocks will spring back to their original position, and that's the energy that's kind of released and propagated through the crust. As you can see here, there's a fault line forming right here in California. This is 2 satellite images before and after an earthquake, and you can see major changes to the land surface as a result of plates moving. So here's a good example of how an earthquake occurs. So we'll start off with this image. Okay, there's a fault line right through the center, right here. And this block wants to move in this direction, and this block wants to move in this direction. Okay, and as this happens, right now the fault is locked, so it can't move anywhere. So over time, as those plates kind of want to move, but the frictional forces are preventing it from happening, they'll start to buckle and build up a lot of stress. Okay, and so you'll see kind of like the land rise in certain areas over here. But over time, there'll be enough pressure that'll overcome the frictional force holding the fault together, and then boom, you get an earthquake and a lot of movement. And that's shown by this kind of out of focus image here, earthquakes occurring, it's all dangerous. And then you get to here, and the process kind of repeats itself over and over again. And here what you see is displacement, and there's been movement along the fault, and you can measure that. Many earthquakes are preceded by foreshocks, meaning that like before a big one occurs, sometimes there can be smaller earthquakes before that, although it's hard to predict. There are, however, after there's a major earthquake, there are a lot of aftershocks, and those are sometimes major earthquakes after the big one. And the reason for that is because once you move, or a crustal block moves after an earthquake, the fault zones have to adjust to that new movement, and the new movement causing new pressure points and areas. So everything kind of has to adjust for a while and move until all the faults are kind of locked in place. The YouTube video that's attached to this slide shows a pretty cool major earthquake in Chile and all the associated afterfaults. Okay. One of the major fault lines we have in the United States is the San Andreas fault zone. And this fault line kind of goes right through California, Western California, and goes through San Francisco. And just east of Los Angeles. And so whenever there's movement of the Pacific plate, so this portion of California is part of the Pacific plate, which is moving northward, it kind of shears along the North American portion of California. Eventually, over geologic time, over millions of years, this portion of California will shear off and become like a linear island in the Pacific Ocean. Another area where you can have a lot of earthquakes is at subduction zones, where you have a subducting plate, typically ocean, lithosphere, kind of subducting down into the mantle. And we have a convergent plate boundary, so these two plate boundaries are kind of running into one another. What occurs here is a lot of pressure buildup, specifically right here on the surface of the subducting plate and on the edge of the overriding plate. And that's where the earthquakes occur. And these are some of the largest earthquakes on Earth. Some of them occur really deep, up to like 400 kilometers. You can detect these earthquakes and the seismic waves that come off of them. And so here are some of these are the strongest earthquakes on Earth. They occur in these areas where there's a subduction zone, and we call those Megathrust Fault. Okay, so seismology is the study of earthquake waves. And earthquake waves is a way of understanding the energy that's released after some slippage and displacement has occurred. The way scientists record earthquake waves is by using a seismograph, and that kind of records the vertical and horizontal movement that occurs in the Earth's crust. Okay, so that record is called a seismogram. Okay, I have a YouTube video that follows along with that. But here are some examples of those seismic waves. These first two here, P and S waves, those are called body waves. So that's a primary wave and secondary wave. Primary waves arrive first at the seismograph, then secondary waves follow. And then surface waves arrive last. They have the slowest velocity, but they have the highest amplitude, and these are the ones that cause all the major destruction. So here's a seismograph. See how it's kind of anchored to the bedrock. Okay. And then what you see here is there's a pivot with a wire, and it allows for kind of side-to-side movement. All right. And then here's a drum that rotates, and it rotates with time. And there's a pen, and essentially if there's any horizontal movement back and forth, the pen will pivot on that and then record that movement on this rotating drum of paper. Okay, and so the larger the seismic wave, the kind of larger the amplitude of the line. So back and forth, back and forth. This would be a major earthquake, and then kind of like, non-existent. It's like, I guess, if you take like a lie detector test, Okay, so I mentioned the body waves. This is one type of earthquake wave. The first type are primary waves. We call them push-pull waves. There's a push-pull motion to it. Imagine you have a slinky, hold it in one hand and attach the other end to the wall, and then give it like a Hadouken, right? Like just push it, and then you'll see that you'll compress the slinky, and then it'll expand and compress and expand and compress, and that wave will travel all the way to the wall and bounce back towards you. That's a primary wave. Okay, primary waves have the greatest velocity of all earthquake waves, so they arrive at the seismograph first, and they travel through solids, liquids, and gases. Secondary waves are a type of body wave. They arrive second, okay, because they have a slower velocity than P waves, and their motion essentially is like if you have a rope attached to a wall and then you move it up and down, this kind of S shape. And that's how it progresses through the rope. Okay. Interestingly, S waves do not travel through solids. And then the last are surface waves. And surface waves kind of show complex motion. You can have two different types. One is like kind of this orbital type motion, like as the energy kind of passes through you, it makes the material move as if water in the ocean. A lot of people, after experiencing a major earthquake, will say they felt like they were on the ocean, and they might get disoriented or dizzy, and that's because of surface waves that move through the crust. Another type of surface wave kind of shears material side to side. If you can see that here, kind of snakes through the surface. These two cause the most damage, and that's what causes buildings to fall, a lot of property damage, and a lot of loss of life. All right, and they arrive at the seismic station last. They're the slowest velocity of all waves. Okay, so the focus of an earthquake is the place where the earthquake originates. Okay, so here, if we have a cross-section of the crust, for example, here is the fault zone. Right down here is the focus. That's where the slippage kind of begins. And then the epicenter is the spot directly above the focus on the surface of the Earth. And humans care about that because we live on the surface of the Earth. And that's the closest spot on the surface of the Earth to the incoming wave fronts of seismic waves. Okay, these circles that surround the focus, those are wave fronts that are traveling in 3 dimensions away from the focus. And so that's how those seismic waves travel. And so the way we locate earthquakes on the Earth's surface is by using the difference in arrival times between the primary and secondary waves. Okay, they travel through, adjusted for the different materials that they're moving through. You can figure out the velocities of the primary and secondary waves, and based on how long the time lag is between the arrival of the first P wave and the first S waves, you can calculate the distance you are from that earthquake from one seismic station. Okay, but so say you have a seismic station over here. Once that first P wave arrives, you can calculate your distance to the epicenter. Okay, so here's the fault, there's the movement, here's the focus, wave fronts, and here's the epicenter directly above the focus here. So let's pretend there's an earthquake that occurs somewhere out west, right? Scientists won't know where it is. But there's 3 seismic stations, one in New Mexico, one in California, and one in, what is that, Utah? Okay, we'll say Utah. So what you can do is based on the arrival of the first P wave and S wave. Think of it as like, say there's 2 people driving. Let's keep it in Florida. You're on the turnpike going south to the Yeehaw Junction. Okay, and if one of the cars travels at 90 miles an hour, assuming you don't get pulled over and get a ticket, and you don't have to stop for gas or bathroom, and you go to the Yeehaw Junction, right? And then the second car travels at 60 miles an hour. Which one's going to arrive there first? Obviously, the faster car. It'll arrive there first, and maybe it'll arrive like a minute or 2 minutes before the second car, right? But if you travel a longer distance, like say you go to Miami, that time lag will be longer. And without knowing that these 2 cars have departed from Orlando, if you know their velocities and you know the time lag between them from wherever they arrive, say they arrive at Miami, then you can calculate how far they came from, and you could pinpoint if they were traveling on the turnpike, then they came from Orlando. Okay, it's the same deal with seismic stations. So here, this seismic station received both the P and S waves. It calculated the distance the earthquake is from the station, and what you can do is draw a circle with the radius of that distance. So say it's 3,000 kilometers away. So you have a radius of 3,000 kilometers, then you draw a circle all around it. So you can't really pinpoint an earthquake with one seismic station because you have a circle and the earthquake could have occurred at any point in that circle, right? So then you draw another one, and then that circle will create that kind of Venn diagram where it intersects at 2 points. And that's why you need a 3rd seismic station. And when you draw the circle around the 3rd seismic station, all these circles will intersect at 1 point, and that's the earthquake epicenter. That is triangulation. So whenever you see that in the movies, we're like triangulating your position. Essentially, they're doing this. All right, here's just another example of an earthquake occurring over here. Okay, and then here are the seismic wave fronts moving away. Here's the arrival of the P and S waves. Okay. Here's the arrival at the first seismograph, number 1, closest to the earthquake. arrival of the first P wave, then here's the arrival of the first S wave. And then you measure this distance, that's in time. This is about, let's say, what, 1 to 3 minutes. So scientists have kind of constructed time lag velocity diagrams, and 3 minutes will translate to a certain distance. So then you can draw that circle around seismograph 1. It makes sense. It's not that far away, so maybe it translates to like 400 kilometers or something. Here's seismograph 2, and if you notice, the time lag is larger between P and S waves. Here it's almost about 5 minutes, okay? So that means the circle you're going to draw around seismograph 2 is going to be really large. And it makes sense because it's further away from the earthquake. And then at seismograph 3, the P waves have arrived, but the S waves have yet to come. Okay, they're still traveling through the Earth's mantle before they get to that seismograph. Okay, so how do we determine the size of an earthquake? Earthquakes have been happening for way before humans are around, and once we're around, we're like, what's that? The gods are angry, right? But they've been happening for a while, and people have been interested in kind of being like, well, how big was that earthquake? And a very early scale was the Mercalli Intensity scale. It's been modified. It was developed by the Italians initially, and it's based on the shaking at a given locale and the amount of damage that exists there. Okay, it can be subjective because it depends on the metropolitan area that you're in, how well built the houses are, how many people live there. So here, for example, here's an intensity map of the Northridge earthquake, which was a magnitude 6.7. We'll talk about what magnitude is later. But here's the intensity map, and this is how it was felt in these areas. So here's high intensity, lots of damage, a lot of people felt it here. A stronger earthquake in terms of magnitude hit Nisqually, Washington, probably fewer people there. And so the intensity map wasn't too strong based on property damage. There isn't as many people. It's not as high as dense. So despite the fact that this one was stronger, it's lower intensity. All right, and here's another seismic intensity map of California. So here are those major metropolitan areas in Santa Cruz and San Francisco, and they felt the highest intensity. A more objective way of determining the size of an earthquake is called the magnitude, and I kind of mentioned or used that earlier, but it's based on the Richter scale. Okay, so it's completely based on the amplitude of the largest seismic wave, which are typically those surface waves. So here's some data collection of seismic waves arriving at a seismograph. Okay, and then here, see that is the largest surface wave amplitude. And so what you do here is you go to the scale and you measure it, and you go, okay, 22 millimeters. And then you calculate the distance you are from the earthquake. So in this case, here's the scale, right? This right here is the scale. And then you input 2 points of information. You input the amplitude, and you draw a dot right here. And then you go over to the distance you are from the earthquake. Here, the example just shows it's about, looks like almost a little over 200 kilometers away. Then you draw a straight line from these 2 points. I know that's not a straight line. And it goes right over magnitude 5. So this earthquake was a magnitude 5. So it takes into account the distance you are from the earthquake and the amplitude of the largest seismic wave, right? And it makes sense because if you were closer to the earthquake, that means you'd scale down over here, and you'd probably have much higher amplitude over here, but the same earthquake will cross through the same magnitude, okay? And the thing about the Richter scale is that it's based on the logarithmic scale. So when you compare different earthquakes, and this is what you typically hear on the news, the epicenter was in Mexico, and the magnitude was 7.0. If you compare two different earthquakes, one let's say that's a 6 and one that's a 7, that's a magnitude change of 1. And what that essentially means is that the earthquake that's a magnitude 7 is 10 times more ground shaking than the magnitude 6. and 32 times more energy was released with just a magnitude change of 1. The strongest earthquakes that hit Earth are at those megathrust faults. So the most recent one that was absolutely devastating was the Tohoku earthquake in Japan in 2011. That was a 9.1, I believe. We can double check in a little bit. But a 9.1 compared to a 6, that's a magnitude change of about 3. So that earthquake was 1,000 times more ground shaking than a 6. So the Richter scale kind of, when you're comparing earthquakes, changes very rapidly. And scientists later developed the moment of magnitude scale. This is for those really strong Tohoku earthquakes. And that measures the amount of displacement that occurs when there is an earthquake. You can go back and look at how much a fault is moved and then use that to determine how strong the really strong earthquakes are. Just so you know, this guy in this rickshaw over here, he does make it. Look, he dives off at the last second. Okay. All right, here are the annual earthquake occurrences based on magnitude. Remember, our Earth is dynamic. It's moving. We've got plates. We're surfing on these plates, and they're moving every single day. There are earthquakes all over the Earth. Okay, if you go down to the lower magnitude earthquakes, between a 2 and 3, between 2 and 3, there's 1.3 million earthquakes every year. Okay, so that's more than a few a day in different parts of the world. Okay, this is globally. Between 3 and 4, this is when you start to feel it. These are minor earthquakes, 130,000 a year. Here are the light earthquakes between 4 and 5, 13,000. Moderate earthquakes, we have 1,300 a year. Between 7 and 6, this is when it starts to get dangerous. Strong earthquakes, 134 globally a year on average. Between 7 and 9, major earthquakes cause a lot of damage. There can be a lot of death, 15 of them. And then the really bad ones, between 8 and 9 and 9, we usually have 1 a year. Sometimes we have, some years we have 1 that's over a 9, and other years we don't. All right, some of the notable really large ones. Chile had one that was 9.5. Japan's Tohoku earthquake was 9.0. Sumatra in 2006 had one that was 8.6. Okay. All right, so this is the topic you guys all want to talk about, earthquake destruction. All right, so the factors that determine the damage that occurs from an earthquake really depends on how strong the earthquake is, how long those vibrations are, what did you build your buildings on, the nature of the material underneath the ground. That's really important. And also the design of the structure. Okay, this can be pretty devastating. Imagine this was your house, your apartment. Oh my God, I lost everything. So ground shaking causes a lot of the damage and brings down the structures. If you build your buildings on loose, unconsolidated materials, as seismic waves travel through that, it actually amplifies those seismic waves. So it makes the earthquake stronger. Okay, here's an example of some buildings in Japan just toppling over. They look like mini Lego pieces that you might step on. But they toppled over because they built it on just essentially unconsolidated material. A lot of the newer buildings have to be anchored to some sort of bedrock, and that helps protect the buildings a little better. Also, if you're in loose material that's filled with water, liquefaction can occur. That's essentially like quicksand. I don't know, for some reason, like my whole life I've been worried, or maybe as a child I was just worried about quicksand. I blame Princess Bride. I thought like that I would run into that more often in my life, but not once, not a single time. So it's just a fear that I wasn't supposed to have, really. But anyways, this can happen during an earthquake. And what happens is, as the ground is shaking and the seismic waves are traveling through the saturated material, it turns into a fluid, so things can just fall into it instantaneously. And there have been California ranchers that have complained that they lost cows due to liquefaction. Okay, imagine that, a cow just sinking into, a slurry of sand. It can't dig its way out because it's got hooves, right? Underground things can float up to the surface. Okay, so that septic tanks and sewers and stuff like that. Earthquakes can also cause landslides and ground subsidence, so stuff can sink, and also fires. The 1906 earthquake in San Francisco, basically it ruptured gas lines, and that caused fires, and about half of San Francisco burned down in 1906 as a result of that earthquake. Here's some more damage that you can observe here from an earthquake in 1964 in Alaska, buildings toppling over. Here's a sand volcanoes as a result of liquefaction. So that can happen here. Go on YouTube and Google liquefaction Japan. A lot of cool videos will show up of sand kind of coming up from the cracks on the street. In New Zealand, there have been earthquakes there where cars will just kind of fall into muddy areas as a result of liquefaction. But essentially here, the water and the sandy layer material will shoot up out of the ground and form these little sand volcanoes. All right, so earthquakes can also cause a lot of problems to coastal communities because they can generate tsunamis. Okay, the first time this occurred and was kind of sensationalized in the media was in 2004 when there was a Sumatran, there was an earthquake off the coast of Sumatra. It was the day after Christmas, imagine, in the morning. There was a major earthquake there. It's a Megathrust Fault. There's a subduction zone. And so not only did the people have to deal with that earthquake and the damage from that, but what happens in the subduction zone is the overriding plate moves forward, right? There's displacement and there's movement. So think of, hundreds of kilometers of lithosphere underneath the ocean water moving forward. And that generates a tsunami, a huge wave and a series of waves that can come in and flood low-lying areas. Okay, the one that occurred in Sumatra was one of the deadliest natural disasters to ever occur. In 2011, there was another major one in Japan. The Tohoku earthquake created waves that were 40 meters high. Click on these videos. It shows you footage of essentially what's going on here. Look at these before and after pictures of this Japanese coastal village. Okay, this was the one in Sumatra. Guys, 230,000 people died. Okay, the population of Orlando proper is about 270,000 people. So, basically it's an event that occurred where an entire city of Orlando, everyone just dies. So this was really devastating. Sumatra was hit really hard because it's very low-lying. The way to escape a tsunami or an incoming tsunami is to go to high ground. Because essentially it's water that just kind of comes in. It's not like in the movies with this giant wave coming in. It's more like a sheet of water that moves in really rapidly and just destroys everything and inundates everything, and you just get hit by it and drown. There's a lot of debris. So yeah, watch these videos. You can fall into a rabbit hole of tsunami footage from these events. Okay, and then this was the Japanese tsunami. Very sad. Lots of people died. In Japan, about 11,000 people died as a result of that tsunami. And there was also the Fukushima nuclear power plant meltdown as a result of that tsunami as well. Okay, so this is how it forms. All right, so here's the subduction zone. You have the subducting plate. Here's the overriding plate. So when there's movement, essentially what happens is the overriding plate kind of moves forward like that, and that generates that tsunami. It's kind of like being in the kid pool of, kid area of a community pool, and you're just shoving these giant waves at all the kids, knocking them over, and you're no longer, allowed to be in the community pool anymore. Jeez. Anyways, so yeah, it's like that. They travel really quickly. They go in the open ocean, in the deep ocean, they travel at like 800 kilometers an hour. But if there's an earthquake off the coast of South America, it still will take about 12 hours before it hits Honolulu. The Aleutian Islands, here's another subduction zone. That'll only take 5 hours before hitting Honolulu. And if there's a tsunami generated off the coast of New Guinea, that will also take 10 hours, okay, before it travels across. The Pacific Ocean is pretty big. Now, the reason why the tsunami in Indonesia was so bad is the Indian Ocean basin is smaller, so people had less time to kind of react or be warned of an incoming tsunami. So earthquakes occur in specific areas, okay? There are these belts. 95% of the energy that's released from earthquakes occur in these narrow zones. This is one major one, the Circum-Pacific Belt. There's a lot of subduction here, a lot of ocean plate subducting underneath continental crust. Okay, here in Japan, subduction along where New Zealand is, and a lot of the islands here. See, here's the smaller Indian Ocean basin, kind of goes out here, it gets cut off, but that's where Sumatra is. But this is where the earthquakes are. In fact, the reason why we know the tectonic plate boundaries is because we essentially just plot the locations, the epicenters of all the earthquakes, and it outlines the boundaries between the tectonic plates. Here's another major zone of where a lot of earthquakes occur, and that's because of mountain building. We call that the Alpine Himalayan belt. So what about earthquake prediction? Check out this dog, look at him. He kind of predicts the earthquake coming before it actually hits. My guess is that dogs can hear the seismic waves approaching, and that's why they freak out before you actually feel the seismic waves. In terms of a short range prediction, meaning like, hey, tomorrow's weather report includes an earthquake, no, that's never going to happen. You can't really, I mean, that's what scientists are working on now. I mean, giving you an exact hour when an earthquake's going to hit is very unlikely. So short-range predictions are not possible. Long-range forecasts, they are possible, and scientists give them. For example, there was an earthquake that hit Port-au-Prince, Haiti in 2010, and a scientific paper came out 3 years before that predicting even the magnitude of that earthquake, and they were spot on. So the long-range forecasts are kind of like, hey, in this region, there's going to be an earthquake of this magnitude in the next 25 years. Now, I know that probably sounds like, oh, big whoop, next 25 years, how is that going to help? But it does, because that allows local governments, cities, and urban areas plan for the future, right? If they know the size of an earthquake that's going to strike at some point, they can have their buildings and structures be able to withstand the earthquake of that given magnitude. And so one way of kind of predicting earthquakes is by finding seismic gaps. So here is Sumatra. This was that 2004 earthquake. By the way, they made a movie on this event called The Impossible, so you can watch that too if you like. But here's that occurred in 2004. Magnitude 9.2 was a biggie. Okay, 2005 there was one along this portion of the fault. 2007 there was one here, and in 2000 there was one over here. So essentially, this ocean plate has moved all along this fault except in this seismic gap. So imagine this has moved forward here, here, everywhere except here. The fault is locked here, and so this is predicted to be the next area where the next earthquake will be. So beware, Padang. There's going to be another earthquake at some point. Very strong one. We also use paleoseismology to help with earthquake prediction. And what this is this really just studies the location, size, and timing of prehistoric earthquakes, meaning certain faults will kind of not be active anymore, but they leave behind traces of the hundreds of thousands of years when they were active, and so you can kind of predict how often they occur and how often large earthquakes occur. So that's paleoseismology. Okay, so let's shift gears into the Earth's interior. Okay, most of our knowledge of the interior of our Earth comes from studying P and S waves as they kind of propagate through the interior of the Earth. The velocities and the travel times of P and S waves vary depending on what material they move through. If the material is more rigid and compressible and hard, the velocities of these seismic waves will be faster. If the material is kind of soft, close to its melting temperature, a little more plastic, I guess, velocities will decrease. And if the material is a liquid, for example, S waves won't travel through them. S waves only travel through solids. So seismic waves can reveal a lot of information about the interior of our Earth. Here are some of the paths that these seismic waves go through as they kind of move through the interior of the Earth after there's an earthquake. So for example, P waves, they'll move, their velocities will slowly increase as they go through the different layers of the mantle. And when they hit the outer core right here, which is a liquid, by the way, the velocities drastically decrease. And so there's some refraction going on of those waves. S waves will completely bounce off. All right, and we know this because we have a lot of scientists set up their seismographs on different sides of the Earth, and there'll be a shadow zone where there's no seismic waves because they're being kind of refracted or even being reflected away when the earthquake's occurring on this side of the Earth. Okay, so what did all this seismic study reveal about the layers of our Earth? This is kind of a review for you guys, but we can kind of categorize the different layers of our Earth based on two broad categories. One is layers based on chemical composition, and then the layers of our Earth based on physical properties. So if we start off with chemical composition, let's start off with the crust. That's that thin, rocky outer layer of our Earth. It varies in thickness from to thinnest of about 7 kilometers on average, and those are in oceanic regions, so that's here. Okay, ocean crust is very thin in comparison to continental crust. All right, continental crust, that averages 35 to 40 kilometers, but in certain areas, it can be over 70 kilometers, like the Peruvian Andes or the Himalayas. Okay, those mountainous regions, you can have it very thick, very thick. Okay. The continental crust, which is this right here, so it's this portion of our outermost layer, it's made up of low-density silicate rocks. Okay, they have a lot of light silicates in them. Its average density is 2.7 grams per cubic centimeter. And it's mostly made up of, on average, we'll say granitic in composition. And it can be very old, up to 4 billion years old. I think the oldest rocks are about 3.8 billion. There's a lot that are 3.5, 3.4, 3.2. So the continental crust is really old. All right, that's this portion. All right, and then the ocean crust, that's basaltic in composition. So that's a little more dense. So when we have a convergent plate boundary, when these two materials collide, the ocean crust is going to sink because it's denser. All right, 3.0 grams per cubic centimeter. And the other crazy thing about ocean crust is that the oldest ocean crust is only about 180 million years old. That's a lot younger, magnitudes much younger than continental crust. And the reason is because it subducts into the mantle where it's then destroyed or reworked, recycled. Okay, so that's the crust. The crust is made up of, either continental or ocean crust, slight variations in density. The mantle below that, that's made up of also silicate rock, but it's much denser. It has more iron and magnesium in it, so we'll refer to those as kind of denser, heavier silicate rocks. Okay, most of the composition of the upper mantle is called peridotite. It's a type of rock with a lot of olivine in it. Okay, and the mantle is the majority of the Earth's interior, 2,900 kilometers below the crust. So that's basically from here all the way down to the outer core. Okay, there are a number of different layers, and we know these layers exist because the velocities of seismic waves either decrease or increase in these layers. So there's the upper mantle here. Okay, here's a transition zone, so there's a change in the minerals in the mantle here. And then here's the lower mantle that goes all the way down to the outer core. And then the core itself, that's below the mantle. In terms of chemistry, it's iron and nickel. Okay, it has the highest average density, 11 grams per cubic centimeter. Okay, and it has a radius of 3,486 kilometers. All right, so if we look at the Earth's layers based on their physical properties, we can break it down into the most outer layer is the lithosphere. And the reason why the lithosphere kind of gets its distinct properties is because it's cool and rigid. Those are the lithospheric plates that are kind of moving, bumping into each other, grinding next to each other. And when those move, that's what caused those earthquakes. That includes the crust and the uppermost mantle. And typically it's about 100 kilometers thick. All right, below the lithosphere is the asthenosphere. This is exclusively in the mantle. It's in the upper mantle, and it goes from the bottom of the lithosphere to about 660 kilometers. Okay, and the mantle rocks here, or the peridotite here, is very close to its melting temperature, so that kind of weakens the rock. It gets hotter here, so it weakens the rock, and it's easily deformed, and it's capable of flowing and moving. Okay, and so essentially, because of the differences in the physical properties of these two layers, the lithosphere kind of floats or sits on top of the asthenosphere and is allowed to kind of move as a result of the soft and weak layer that's below it. Then below the asthenosphere is the mesosphere. This is the lower mantle. Now you're so deep within the Earth, the pressure is so great that the rigidity of the mantle increases. And so the rocks in the mesosphere are very hot, and they're capable of flow, but very gradual and very slow. So it's a more rigid layer, and that goes from 660 to about 2,900 kilometers. Okay. And then you hit the outer core. And the outer core is liquid, all right, about 2,270 kilometers thick, and you have convective flow of the metallic iron within the outer core. That generates our magnetic field, protects us from cosmic rays. All right, and then we have the core, the inner core, and that is the only thing that's an actual sphere. It actually rotates independently of Earth's rotation. And it's a solid. It's 754 miles in diameter, and it's iron and nickel and has the highest density. So there you have it. Over on this side, these are the Earth's layers based on chemistry. The crust, very strong rock layer of light silicates mostly. The mantle, which are also a silicate rock, but a little heavier, higher density in comparison to the crust, more iron and magnesium. And then the core itself, the core is iron and nickel. And then if we can look at the Earth's layers based on the physical properties, and then we have the lithosphere, all right? That's this right here, this brown area here, on average 100 kilometers, okay? And that consists of ocean crust, continental crust, and a portion of the upper mantle is part of the lithosphere. And that's what makes up those lithospheric plates. Beneath that is that very weak area, the asthenosphere, goes down to about 660 kilometers. Then below that, this is the lower mantle. Okay, here's the lower mantle. All right, then you go to the outer core, which is liquid, and the inner core, which is solid.